To get quality signals, we also need to make a ground wire. The necessary components are an EIB, wire strippers, solder, Mil-Max connectors, heat shrink, insulated wire, and flux. When dealing with the flux and hot solder, we want to use gloves. Cut a piece of insulated wire to 7 centimeters. Using the wire strippers, remove about 4 millimeters of insulation from each side of the wire. Make sure you're using the correct groove of the strippers so as not to remove any wire along with the casing. Let's now cut 2 rows from the Mil-Max connector. It's common to break pins while cutting, so aim to cut 3 and remove the broken row. We can now solder the Mil-Max connector onto the wire. Let's first coat the wire and the pins of the Mil-Max connector with flux. This helps the soldered parts adhere to one another. Using the soldering iron, we can now add a drop of solder to the wire. The soldering iron can be very dangerous, so be sure to get a thorough in-person tutorial before attempting this. Now, place the Mil-Max connector onto the wire such that the drop of solder sits between the 4 pins. Use the soldering iron to further melt the solder between the pins, forming a strong connection. If the parts are soldered properly, they should not detach when pulled apart. We now cover the exposed wire using heat shrink. You should remember how to use heat shrink from when we built the cannula. The other end of the wire will be soldered to the EIB. Oftentimes, however, some wire must be removed before it will fit through the EIB ground hole. After determining how small the wire has to be to fit, cut off the excess. Place the wire through the ground hole. Using the techniques we learned before, apply a drop of solder to both sides of the EIB where the wire protrudes. Let's attach the EIB to the drive holder. We'll need our EIB, a clip to hold it, and a T-shaped screwdriver. Attach the clip to the EIB as shown. Make sure the hold is secure. Connect the clip with the EIB to the drive holder. The extra nut adds stability. Use the screwdriver to lower the EIB to 2 centimeters above the top of the drive body. The next step, called pinning, is where we insert the tetrodes we made into the drive. We'll need our tetrodes, usually kept in a box, gold pins, a roll of tape, and 3 types of forceps. We begin by inserting the annealed end of the tetrode into the shuttle tube. It is important that the tetrode does not kink below where it enters the shuttle tube. If it does, grab a new tetrode and start over. Pinning is often regarded as the most difficult step of drive building and requires a lot of practice. Also be sure to take breaks, support your wrist, and sit up straight to minimize joint and tendon strain. Once the tetrode is inserted far enough, you should be able to see it protruding from the cannula. Rotating the drive nearly upside down, we can see the unannealed end of the tetrode near the EIB. Placing the roll of tape beneath the drive holder can be helpful when trying to focus the microscope on the wire. Please be aware, however, that this position causes the tetrodes protruding from the cannula to be very vulnerable. Use caution to refrain from bumping and kinking them. Here, I trim the 4 separated tetrode wires at an angle to help prevent them from sticking to one another. Our goal is to get each of the 4 wires into a separate hole in the EIB. If your tetrode kinks here, that is okay because the kink is above the shuttle tube. However, trying to pin with a kinked tetrode is exponentially harder, so it's likely easier to start over. While I show myself pinning, I'll share a few useful tips to hopefully make the process easier. If you are not focusing on pinning at this point, please feel free to skip the next few minutes. Learning how to focus the microscope is crucial for this step. Good lighting that reflects off the tetrode also enhances visibility. If you are struggling to separate the wires, tapping them gently against the EIB can help. Also pay close attention to where I hold the wire with my forceps. Holding the wire too far away from the tip limits control, but holding too close can increase the likelihood of kinking. Experiment to find the sweet spot. Finally, always use carbon tip forceps when handling tetrodes. Before you begin pinning, it is also worth noting that each shuttle is deterministically mapped to a set of holes in the EIB, so make sure you're paying attention to the numbers written on the EIB. We can now use the sharp forceps to place a gold pin in each of the 4 holes. Using the broken forceps, clamp down on the pins to press them into the holes. Be careful not to trip the wires while doing this. As the pins are pressed down, they scrape off the casing of the tetrode wire, effectively creating an electrical connection between the tetrode and the EIB. Now it's time to glue each tetrode to its corresponding shuttle. Similarly to how we glued the shuttle tubes, deposit a small drop of glue to the junction between the shuttle tube, shuttle, and tetrode. The EIB is ready to be lowered onto the drive body. Let's grab the T-shaped screwdriver. Slowly turning the screw, we lower the EIB. To properly align the EIB with the drive body, the EIB must also be rotated gently. Make sure there is sufficient slack in the tetrodes before rotating to prevent them from snapping. Once the EIB is completely lowered and its holder has been removed, we can trace the edge of the EIB with epoxy to secure it to the drive body. Once again, be careful to avoid dripping epoxy elsewhere, such as on the screws. The next step is final cuts, during which we cut the tetrode at a 45-degree angle. For this, we'll need specially designated final cut scissors, which are identifiable by a label with the date or the word new. Final cut scissors are not to be used for any other purpose, so that they remain sharp. A good final cut is straight with no appendages. On the left is an example of a good final cut. The 2 on the right are poorly done because of the wire casing left hanging from the ends. If you're finding it hard to view the quality of your cut, try repositioning the light source, putting a piece of white paper below the tetrode to reflect the light, and viewing the cut from different angles. The length at which to cut the tetrodes will partially depend on the experiment, as some brain regions are more superficial than others. Tetrodes must be short enough to retract fully into the cannula, but long enough to reach the region of interest. Once the tetrodes are cut, they're ready to be plated. Plating is the process during which we coat the tips of the tetrodes in gold to enhance conductivity. We'll use this adapter to connect the drive to the plating machine. Correctly securing the adapter to the drive is vital so that the drive does not fall. The adapter connects to the EIB as shown. When it is on correctly, the negative space between the adapter and the EIB should be balanced. Because the tetrodes are lowered for plating, drives are very vulnerable at this stage. You may notice that the tetrodes are not visible in my example. This is because I am demonstrating with a previously implanted drive, so this region will look different. Here's the setup of the plating machine. We secure the adapter with the drive, connect the cables, add gold solution to the well, grab a beaker of deionized water, and be sure to wear gloves whenever directly interacting with the gold solution. In order to plate, we carefully lower the tetrodes into the gold solution. Twisting this screw allows you to raise and lower the drive. Be sure to lower the drive such that all tetrodes are in solution, but none are touching the bottom of the well. Also ensure that the cannula does not enter the solution. In order to avoid mistakes, such as lowering the drive when you're trying to raise it, it's best to turn the screw slowly. Once again, the tetrodes are not visible on this example drive, but will be on yours. After unplugging the computer, we open the Nano-Z program. Use the following settings to clean the tetrodes. If you are plating a 32 tetrode drive, choose the upper left setting that says 32CH. For a 64 tetrode drive, choose 64CH. Press the autoplate to begin. As the program runs, impedance values are output for each channel. Values outside the 1 to 3 megaohm range may indicate dead channels. However, if you are seeing a surprising number of dead channels, or no values at all, it's worth double-checking the connections and perhaps restarting the Nano-Z program. After cleaning, we change the settings to begin plating the tetrodes. If we know that a channel is dead, we can unhighlight it on the black map above. We now begin our cycle of rinsing and fine-tuning. To rinse, dip the tetrodes in DI water for 10 seconds. Fine-tuning is similar to the previous step, but uses a weaker current. The settings are as shown. Whenever the program runs, an output window such as this one appears. Keep rinsing and fine-tuning until most of the values in this column are 0, meaning that no intervention was needed to get the impedance value in the target range. Because each tetrode has 4 channels, a 64 tetrode drive actually has 256 channels. For a 64 tetrode drive, we just plated 64 channels. We must thus move the connectors and repeat the aforementioned plating process 3 more times. The exact mapping of how to rearrange the connections will not be shown here, but I will highlight a few key points. Make sure the silver line is facing forward and the male Milmax connector is 1 row back. When swapping the connections, always hold the adapter instead of the drive, as any pressure on the drive can cause it to detach and fall. Swapping the connections will also require rotating the adapter at some point. To remove the adapter, carefully wedge a screwdriver between the adapter and the EIB and rotate. This motion helps to lift off the adapter without damaging and bending parts. After plating, always be sure to rinse the tetrodes in DI water. We also want to make sure that the computer is plugged back in. The day before the drive is implanted in the animal, another few cycles of fine-tuning and rinsing should be conducted. Let's see what we've created. We now have a drive that looks similar to this. When we rotate a screw, its corresponding shuttle travels vertically. The shuttle is connected to the tetrode. Thus, rotating the screw allows us to lower the tetrode into the brain. The tetrodes are ready to be raised into the cannula. Watch to see how tetrodes move under the microscope. After this step is a great time to map the tetrodes, or make sure you know which tetrode corresponds to which cannula tube. This can be accomplished by photographing the surface of the cannula, and then lowering a tetrode slightly and marking which tube it protrudes from. Before implantation, the tip of each tetrode should be level with the surface of the cannula. Thanks for watching.